Hello, everyone. Thank you for joining us today for the 2025 DME webinar series. We appreciate your time and interest in staying connected with industry experts and the latest advancements in our field. As many of you know, our series is held monthly and focuses on addressing key challenges within the industry, sharing insights, and exploring innovative solutions. Today, we're excited to welcome Richard Gain, the Chief Sales Officer from Servomold, who will be presenting Unlocking the Power of Servo Unscrewing Devices, Complete Mold Integration with DME and Servomold. This session promises valuable insights into advanced mold automation and efficiency improvements that can help elevate your operations. Looking ahead, next month's webinar will feature our own Jeremy Such, who will delve deeper into Hot Runners technology. Be sure to stay tuned for more details and registration information soon. To view our upcoming schedule or to register for future webinars, please visit www.dme.net/webinar and sign up. A recording of today's presentation will be sent to all registrants within a week, so you can review it later or share it with your colleagues. During this session, if you have any questions, please submit them via the chat box. We will address your questions during the Q&A segment at the end. Additionally, our DME sales representatives are always available to assist you after the webinar with any follow-up questions or support. And now, without further ado, I am pleased to introduce Richard Gain from Servomold.
Thanks a lot, Mark. Again, apologies for this technical problem, but we will move straight on now and go straight into our webinar presentation that we'd like to make. So again, thanks a lot for joining. We're going to be talking about unlocking the power of servo unscrewing devices. Before I go into great detail, I just wanted to introduce myself and our team. Basically, I'm supported there in a very nice way by Lucas, Christian, and Christopher. This is basically our whole internal sales project management team. We're all based here in Germany, in Erbach, in the middle of Germany pretty well. And that's the people that you will be speaking with mostly or connecting with for any projects and RFQs and also projects that are up and running. So it's the four of us. And before I go into the exact detail of the case study, which I want to show you all, just a very quick, brief introduction as to who Servomold is. I don't know, maybe some of you already know about us, some of you maybe are already customers, but I'm sure there are plenty of people who don't know us yet. So I want to introduce you. We started back in 1998. Originally, we were with the company iMold, making cold banana gate, tunnel gate inserts. But the owner, Thomas Meister, and managing director, who is still the only owner and managing director, always had a passion for mold control and servos, electrical movements for injection molds. And over the years, I've been working on different patents, different ideas of how one can make all the different movements, which are traditionally hydraulic or pneumatic, either rotational or linear or even index plates, how one can convert all of that requirement, all of those movements into electricity, into an electrical impulse. And in 2012, the name Servomold was founded, company Servomold. And since 22, we've completely split from the iMold. Obviously, that was a partner company. But basically, the Servomold, the offerings that we've been doing has been on the market now since 2012. And we have patented systems for unscrewing units, as well as our own in-house control units, control systems, and of course, motions for linear activation. We've been partnering now with DME in the US and Canada for over 5 years, and looking forward to the next 5 years. So I'll move straight on. What I would like to show you exactly the whole, the basis for this webinar is from quote to final product. We're going to do a case study for an unscrewing device. This is it's an OEM medical company who we're supplying. We've supplied already over 5 molds of this design, and that's how we know exactly what we're talking about. It's a little easier to explain a case study when there's far more detail and information that we already have. But I want to lead up when we're going to be working with any customer. It all starts off with initial RFQ. So an RFQ can be either made jointly with DME. Your DME contact person would help you filling in the RFQ, or they would fill in the RFQ themselves with information from yourselves. And that would be sent to our team of 3 there in the corner, being very, very happy to receive your RFQs. Even happier when, as over in the top right-hand corner, we get all the information that we need. Now, let me just make a laser pointer here. There we go. We do require 3D, or if you don't have 3D, then at least 2D part drawings. We need the resin data sheet. That's essential. The reason that we need that information generally is to be able to calculate how much power, force, torque that we're going to need to move either the unscrewing core or the core that we're going to pull out in a linear direction. You'll see here very, very clearly what sort of information we require. That all needs to be filled out. And of course, the more information we get up front, the more accurate the quotation that we can make will be. And it would also save a lot of time then later. I mean, sometimes obviously customers don't have everything, but even a picture, a good couple of pictures would do of the product if we have the resin data sheet and some dimensions. And then we would be able to calculate the forces. This basically shows very simply how we calculate these forces. As I say, we need to either have an unscrewing torque for each part. We do that, we use our own calculation system, our own little calculator that we've put together for ourselves. We're using Young's modulus. This is basically how we can actually find out how the plastic reacts, how it's not necessarily its stickiness, but we definitely have its shrinkage, and we would have how the material reacts when cold. We do the calculations, and I think that's quite important to mention at the very beginning, that the calculation we're making is with cold situations. So in the worst case scenario, when the mold has been filled and you haven't been able to use the unscrewing for any particular reason, the mold is shut down and it's cold, we need to be able to overcome the shrinkage that has happened over that period of cooling. And we still need to have the motor powerful enough to be able to unscrew however many cores or pull however many cores we're going to need to move. What you can see here on this screen, obviously this is the part that we did the calculation for. We have a very basic schematic diagram of what it is. We put in the dimension, put in the material. We do, and that is written at the very bottom here on the top, we optimize the calculation with our own experience, of course, over the last 13, 14 years. We've made many, many systems now, well over 1,000 systems with all types of different plastics, because obviously every resin has a slightly different reaction to shrinkage, but not just shrinkage, but also to stickiness. In like an HDPE, they tend to be a rather sticky material, and you need to be able to get over that initial movement of unlocking that stickiness from the core. So we put in the information, but we also put in our own experiences, and that would give us at the end then the maximum torque required. And of course, working at maximum temperature. The temperatures obviously make a huge difference, as I mentioned earlier, but that's the cooled parts. That's how much torque we would require. Once we know how much torque each individual cavity is going to require, we then need to start looking into which system we're going to use or which sort of layout we would choose. Now, I'd like to explain the systems that we have a little bit like a big box of Lego bricks or Lego parts. We have lots of standardized parts. Obviously, we don't want to make absolutely every single part of a system from scratch and reinvent the wheel. So we have a lot of standard parts. Of course, with an unscrewing core, every core is going to be different, but we have templates, we have standard parts. And when we know how much torque we require, we would then start to look through which system are we going to take, and that would be based on the considerations that we have to think about. How's the position in relation to the party line going to be? how are we going to eject the part? Is the part laying down outside? Is it standing up? Do we need to unscrew the part? Do we need the core to move back whilst unscrewing, or can we unscrew on the spot and ejector plates move forward at the same time? How many cavities are going to be required in this system? The cluster layout, we call it a cluster layout, but also the pitching. Either it's in a linear, so in a straight line, such as a rack and pinion system, where all the cores would be in a nice straight line. You can pull a rack up nice and straight and unscrew it that way. Or, which was in this particular case, are they in a cluster, a rotational cluster? And for this particular mold, the hot runner chosen was the Moldmaster's melt disc, 56mm, meaning it was a 8-tipped melt disc, meaning that we have a cluster of 8 cavities. And then you, of course, need to calculate or take into consideration the cavity distance. And for this particular case, we chose the multi-system. We call that the multi-system, see here underneath. When we send a quotation, those of you who have already received quotations, there's always a little rendering or picture of the type of system that we're quoting, so that you get an idea what are we actually being quoted here. It can be sometimes a little overwhelming. There's a lot of information in a quotation. There's a lot of writing, a lot of letters, a lot of abbreviations, but a picture, as in a presentation like this, says far, far more than just a lot of writing and a lot of words. So for this particular case, we chose the multi-system, and we take then a few more considerations. So we're going to go with a multi-system. I'll just slip back, and you can see here the drawing that you have. There's a motor on the top. There are gear wheels on the back. Very simple system, what we would call a one-gear level system. It's basically your one motor driving a gear, pinions between each other. There are pinions in between. Obviously, all the cores need to rotate in the same direction, so one needs a pinion in between. Or there's a 2-gear level. And in this particular case, it also makes for a slightly smaller mold with outside dimensions, as you can see. We had a clamping plate of 596, 496. In this particular, it would have been 946. We chose a 746 by 446, quite a narrow mold. Okay. Cavities. Obviously, the width taken into consideration exactly what machine, but I'll get to that a little bit later. This was the chosen system. It was with 2 gear levels. I'll explain that now. As mentioned earlier, there was the Moldmaster's melt disc, 56mm melt disc. That's from tip to tip. So we needed to be able to ensure that our cores were located radially around the melt disc. There are options here as well. There are always lots of options. We have the option of a ratio 1:1. Basically, our drive wheel here in the middle would make 1 full rotation, and our core, our threaded core, would also make 1 full rotation. It isn't a regular option, but there is the option to go to a 1:2. This would be used mostly for a very fine thread, where there's not a lot of torque required, but speed. You have a lot of revolutions to do, which obviously every revolution takes a certain amount of time. And if it's a very fine thread with a very long fine thread, you need a lot of revolutions, taking a lot of time. So in this particular case of 1:2, 1 full revolution of the drive gear would give 2 revolutions of the core, threaded core wheel. In this case, we chose the 1:1. It's a lure lock. Those of you in the medical industry will know lure lock is quite a fast thread. It's got a large pitch, standardized, of course. Makes it a lot easier for ourselves when we know it's a lure, because then we know exactly the pitch and the sizing. However, we still have to keep in mind that there are different resins, and a lure lock or a lure thread in a polypropylene in comparison to a lure thread in an ABS would again be a very slightly different shrinkage. So it's going to be a slightly different size core. Nevertheless, we chose the 1:1 for 48 cavity layout with 1 single drive unit. We know we only need 1 drive unit because earlier we did the calculation We know how much power, how much energy is needed to be able to unscrew each core. And with the 48 cores being unscrewed here, the one motor chosen would be powerful enough to unscrew all 48 cores in the cold position. As you can see here, it's a nice 2 rows of 3. So we have 6 clusters, so 6 complete 8 cavity clusters like that. This is the one that's chosen. Of course, there are options. One could have gone with half and have another motor underneath if it was a far more power needed, if there's far more shrinkage, if there's a different resin. But these are options, and very important decisions need to be made when we do those considerations, that calculations as mentioned earlier. So moving on to the actual details of this particular system, this case study that we made, it's a, like I said, 48 cavities. So we have 8 cores in a cluster. Now, as you saw earlier, we have the 8 cores at the top. There were pinions in between, which you can nearly see here where my red dot is. And we have the drive gear underneath at the bottom of the core. Now, it's a servo mold patented system that we always standardize and that we always use. And I think it's important here to mention exactly how this works. I'm not going to go into fantastic detail, but I'll give you a general idea that unscrewing cores, in servo mold's opinion, need to be driven by a gear at the back, which is not under any radial pressure. Now, the only way we can do that is this gear wheel here. Well, here you can see a nice example of a larger unscrewing core. Obviously, it's not the core that we used in this particular case study, but the principle of how it works is the same, exactly the same. So you have your lead nut and your lead screw. This is the lead screw, this is the lead nut, this is the thread at the bottom that goes into the cavity. We need to drive this core. So we drive it over this gear wheel, a standard core, a threaded core that one could buy from a standards supplier. These gear wheels are usually all part of the one core. We go against that because we realize that this energy that we're putting into these gear teeth not only makes a radial motion, but it also gives a lateral force onto the side of the core. We've taken up that lateral force with these roller bearings. We have one on each side of the gear wheel. You can see them here and here. This is the gear wheel in the middle. That's being turned. Now, by turning this gear wheel is located over these splines to the actual core. The splined surfaces are what is driving the core in a rotational direction. So there is no lateral energies being put into the core. The core is pretty well free. It needs to be free because we want to try and reduce the amount of internal resistance that any other design would otherwise give. As you can imagine, the more internal resistance, and don't forget this is 48 cavities, there's a lot of cores being turned. And if each core had far too much internal resistance itself, we would need to go to an even larger motor. But by using this patented system, we can reduce the size of the motor. The whole thing is very compact. The guide nut, which you see here in this particular example, is held down and in place with this black retaining plate. On this cluster, obviously it's not a four-sided or a rectangular plate, but we obviously manufacture the plate to fit within that cluster. These are the plates holding the guide nut in position that needs to be fixed. Now, very interestingly on this particular case, and this is one of the points that we have at the very bottom, is that these cores are indexed. The customer, the OEM, and this is really a regular occurrence in the medical industry for Lure type parts, any Lure locks, any Lure connectors that are being manufactured. It's preferable to have the injection point on the exact same position of every part. Now, as you can imagine, if you had to try and set that yourselves, that would be extremely difficult, 48 cores to get them all in the exact same position. We do that in advance. We're indexing these cores. The core has a surface, which we manufacture. The gear wheels themselves are manufactured individually. So each gear wheel in each core is 1 unit. And there are, I think it's 15 degrees, correct me if I'm wrong there, 8 cavities, 360 degrees divided by 8. Those would be the degree of difference from one core to the next. So they're positioned, indexed cores from ourselves, already set up so that you will be injecting, or the gate point will be on the same position every time for every cavity, for every part. Needless to say, the whole system is clean room suitable. One of the main reasons that most OEMs and molders are moving towards servo movements is the fact that they are clean room suitable, unlike hydraulic and particularly like pneumatic. And obviously we're giving extremely high precision, within 1/100th of a millimeter positional accuracy of each core. I hope that is clear. Obviously, when we come to the end of my my talk, we can go back to any of the slides. In fact, if anybody is not quite clear on everything that we're showing, I'm more than happy to move back. I can move forward and backwards. So that's the system details. What exactly did we supply? So obviously we supplied 6 complete units like this. In this particular case, however, we supplied the complete B side. This is something becoming more and more popular with a lot of modern mold makers nowadays, where they are streamlining their manufacturing processes more towards industrialization, standardization, meaning that the machine parks are being streamlined, cores and cavities being the main part that mold makers are manufacturing. We are very, very happy, and it's easy for us to supply the plates. It has advantages insofar that we can also assemble and test everything before it goes out to the mold maker. At the end of the day, mold makers nowadays are buying complete hot halves, so it makes a lot of sense to be able to buy a complete cold half from ourselves. Whether this is an unscrewing system or a linear activated system, makes no difference for us. Plate manufacturing is the same. And we have to design, and we're usually very involved in your whole complete mold design anyway, to be able to get this whole system to fit the mold that you're designing. So if we go ahead and carry on manufacturing the rest of the mold, the B plates, even the ejector plates, in this case, the mold maker made their own ejector plates. There are another 3 plates coming onto the top of this. That was made by the mold maker. We're completely flexible and can manufacture whatever, however much or however little that the end user requires. As we can mention, come into a little bit later, we'll supply just a motor if that's all somebody wants. So we're relatively flexible. This particular case study, and this is how we delivered it at the end. 48 cavity B side, all the drive, gears, cores, plates. There was a 10mm stroke, so an unscrewing stroke, 10 millimeters in 0.8 seconds. Those are the sort of speeds that we are achieving with servo control. And total mold cycle time was 7.8 seconds, 48 cavities, fully automatic running, parts in free fall, no robot. So to bring this one to an end, this whole complete process overview, as we have walked through this one particular case study, we first have to work out exactly, so we can say, I have to apologize having lots of writing now on the screen. I know it's always, I much prefer to have pictures. It makes far more easier to be able to explain things, but in this particular case, right at the end, I think there's no other way around, giving a list of all the considerations and actions that were made in this particular process. So there's the task. We'll get the RFQ. What does the customer need? We need that RFQ to be able to show us exactly what the customer requires. We'll need to know the time frame. This is important to know in advance. I can't stress that enough. Time nowadays is always of the essence. No matter what industry we're working on, there's never enough time. Everything has to be done yesterday. So during the RFQ phase and the quotation phase, it is important to keep this whole time frame in mind. I want to add to that, there's nothing written on here about it, but the process the way the process works within Servomold, and our colleagues at DME are well aware of this and will also support you and keep you informed on this. The turnaround time, or the delivery time for a system that we're making, would start after approval of all the drawings. And although we always say this in the quotation stage, we mention it many times, it can we have had situations, they seem to keep cropping up every now and then, where, yeah, you mentioned 10 weeks, how come, where is my system? And the approval took 6 weeks. So I can't stress enough how important it is that the whole approval, that's basically your engineers, our engineers getting our heads together, we'll have team meetings, we'll share drawings. When we've designed it so that it fits your mold and your engineers see our design, check it with your own design, then we need a written approval. That's when we kick off, that's when we start purchasing steel, so we start manufacturing. And that's when the date starts. So I just wanted to mention that, keep that in mind. But back to the RFQ and this whole process, there's the motion profiles. So does the part need specific or special profiles? It isn't just unscrewing. Is there an ejector movement that needs to be done at the same time? Are there slide movements that need to be moved at the same time? It's usually, or it can happen where there are threads, there are threaded cores with a hole going into the side, a venting hole, which actually has to locate up against the thread body. There's all sorts of specialized details that need to be taken into account. There's speed, cycle time requirements. Really important to have that clarified at the very beginning. We can make the system, as you can see earlier, a 0.8 second cycle, a 0.8 second unscrewing time is very, very fast. If that's not necessary, we can do it slower. But every case, it's a case-to-case study. We need to be able to check that out. What is possible? We give those speeds to you in the quotation, but if they're not fast enough, then we have to look back into it, not later. Forces, how much torque is required to make movement? As I mentioned earlier, we go through our calculation. Then there's the molding process. Are there any special requirements during the molding? Are there other movements? Are there, for example, as in the next part, what machines will be used? What sort of automation is going to be used? What size of the machine? How big does the system, or how big can the system be? Is it a tie bar free machine? And there's not such a big discussion, but if it's a small tie bar machine, then we need to be able to make sure that we're designing that system to fit within your mold, your molding machine. Then, of course, there's the hot runner, the pitching. There's always a discussion. We need to be able to make what are the pitching requirements. Usually, we have no problem matching whatever hot runner system can give as far as close pitching is concerned. Obviously, the far further the pitches need to be, the bigger the gear wheels. We will just manufacture the whole thing to fit what you are wanting to use. As I mentioned earlier, it's a robot. Is there a takeout requirement, or is it free fall? Is there an end of arm robot having to go in? Do we need to make the pitching suit that end of arm robot if there's already one made? Maybe it's a mold that's being converted from hydraulic to electric, or maybe it's a new mold, but you're going to be using the same automation, same machines that a hydraulic mold was using. We need to be able to match those pitches that you're using already. And then very importantly is the controller, and I will get to that a little bit more in detail. Obviously, everything that we're supplying with an electric motor, a servo motor, needs to be controlled. And yeah, myself, I'm a toolmaker, the minute I see a couple of cables, it's always a little bit scary. These motors have more than just one cable. There's a couple of cables coming out, a few cables, and we need to be able to control it. We have Servomold building our own control units. A couple of years back, we brought out the new SMC, and I will mention that just a little bit later, but I don't want to take up too much time on that right now. But within this quotation, we also need to be ensuring that we're giving you the servicing and commissioning. Our colleagues at DME will support you in this. We will support them. And obviously, communication is the absolute highest priority for the whole process. is that we're all communicating, both yourselves as a customer, DME as our partners in the US, and ourselves. We need to have a very clear communication within all of us. And the full scope, the scope of delivery can include the service, maintenance instructions, tools, everything that you need to be able to run that system efficiently and safely is supplied when the whole system is delivered. You'll get the instruction manuals telling you exactly how to look after it, how often to look after it, and of course, where necessary, tools to be able to take certain parts apart and maintain them, even a list, recommended list of greases and fats, lubrications that are necessary. Very, very important to have all of that right in with the full scope, so that you can run for many, many cycles and many, many years ahead. That is the case study, and I think I don't know how long I've been speaking for now. It's only 30 minutes. That's good. I'm sorry about that. We started a little bit late. Nevertheless, I wanted to show just a quick overview of everything else that we do supply. We've concentrated here quite clearly on unscrewing. The system that we showed was a system unit, so basically it wasn't a pre-made, but we have unscrewing units like this, which is basically they're not pre-made, but they're pre-designed. We have designs for lay-down unscrewing devices or stand-up unscrewing devices, 1, 2, 3, 4, 5, 6 cavity, depending on what's necessary. And these are pre-designed. Obviously, we can't pre-manufacture anything because we don't know what the pitches are going to be, and we don't know what the cores are going to be, what sort of threads. But we're, like I said, we've got a pre-design, and we can go straight into manufacturing these parts ourselves the minute we know exactly what's going to be required. Alongside the unscrewing cores and the unscrewing systems, we also supply and usually quote this alongside our rotary cooling devices. The cores need to be cooled, usually, and if you're rotating them, then you need a bubbler inside that's going to be able to be rotated. We have a system with ceramic seals fitted, extremely efficient systems that work very, very well. Will move with the core, whether the core's moving backwards during unscrewing or standing still and unscrewing. We have systems for either. And as I mentioned earlier, there's also the possibility, if one has everything else, just a drive unit. We have a motor, we have the gearboxes, and we can supply the correct one when we know the torques and powers necessary to run the mold that you have. These can be often used, of course, for retrofitting from hydraulic when you want to move straight over to electric without having to completely rebuild a mold. Moving on from the unscrewing, so basically the rotational movements of servo motion, we also have linear activators. The linear actuators are basically there as a slide mover, although we've also seen them in other systems moving other parts of molds, depending what the requirements could be. They're extremely flexible. They come in a vast range of sizes, from extra small to extra large. It sounds very easy when I say that, but I think I'll save that for another webinar where we can go a little bit more into linear movements. But these are our SLA. It's a standardized core or slide movement. We have then, and this is new on the market last year, the core pulling units. These are very, very specific units designed for lift and strip mold concepts in the medical industry. Usually, I say medical industry, it can be any industry as long as the part is using or needed a lift and strip concept. Tubular parts being injected on the side, needle valve, where the parts need to be taken, lifted up out of the cavity and then stripped off the cores. These particular units are designed specifically for that, but that is a completely different webinar, which I'm sure hopefully you'll all be able to join in on. Hopefully we can do another one of these later this year, and I can go into more detail of exactly what they are. And again, last but not least, our servo mold control. I want to go straight to that actually and give you an idea of what they really are. Our earlier, what we used to call the SKS controller, was a tabletop unit with a small screen, very efficient, several hundreds of them on the market, all over the world, to be totally honest, quite impressive. But we've changed that. We were receiving obviously a lot of input from customers, what customers would prefer, and it's quite clear that ease of use is one of the top priorities for molders. They don't want to have very highly trained engineers are the only ones who can start up a servo-controlled injection mold. So we've redesigned, firstly, the hardware. We have what we now call the SMC, servo mold control, even that one. They come in 3 different sizes. There's a mini, standard, and a rack. Of course, different amplifiers can be fitted depending on the power required for each different servo motor. The really highlight of these is the user panel. This is a separate, like a pad, basically, with a touch screen where you can control all the movements of the servo. It's connected with a 10-meter cable. The controller itself can go behind the machine. We know that the space is always quite a discussion. We want to make them as small as possible and hide them as best as possible. And of course, our earlier version, which was tabletop, meant you had to have a table next to your molding machine, which wasn't always convenient. So now with these, they can be rolled. They've got their own little wheels they're rolling on, moved out of the way. And the control panel can then be held in the hand. It can be attached to the guard of the injection molding machine, either over the very strong magnets which are fitted to the back, but it also has a little stander and hook system that could also be fitted to the molding machine. They have an RFID touch card or chip, so that whoever is going to be using it, these chips come on different levels, so that different people have different access and availability to change. One of the highlights for our new software in these systems is the fact that adjustments can be made on the fly. And basically, this is quite a leap from standard systems where normally we'd have to stop the molds, stop the process, adjust the motion that you want to adjust, start it up again. Because you lose then process temperature, process time. It's nice to be able to do any sort of adjustments whilst the whole process is running. With this system, we can now do that. As I said, there are 3 different sizes. The SMC Mini is a controller for one motor only. It cannot control any other. It can, however, run several programs, up to 100 on its internal Speicher capacity, its internal memory, the word, will take up to 100 programs. So basically, if you've got a servo or an injection mold with a servo on it, and you only have the one on it, but it only runs for 2-3 months a year, then no problem at all. You can unplug it, put in the next mold that you also have a motor in it, have another program for it, and you can run up to 100 molds individually, one after the other, as you wish. Of course, some molds have more than just one motor. So we have then the standard that can take up to 4 controllers, so 4 regulators or amplifiers, we call it. Up to, I say, because sometimes, in fact, quite often now, the price difference between a mini and a standard with one control panel in it isn't so huge. But if you buy the standard, you have the option later. Obviously, it needs to come back to us because there's quite a lot of wiring involved. But the standard can be upgraded to up to 4 controllers. So 4 motors can be controlled with the standard. And the rack is a very, very similar situation, up to 8. It can be delivered with as few as you wish, but if you know there's going to be more than 4 in the future, then the rack would be the one to go for, up to 8 servo drives. That brings me actually, as far as our products are concerned and the details and technical details of the projects are concerned, brings me to an end. I would like, however, to move on to just a quick overview of the market share where we're working in now. As you quite obviously see, medical pharma is a good 60% of our work now. Packaging is not disappearing, as are many of the other industries are all alive. And we're always very, very happy to work on whatever industry you may be in. It's quite often that these industries tend to swap amongst each other. Fluid control or even pharmaceuticals and packaging come in together. So the most important thing is, if you need to have something servo controlled, servo moved, reach out to us as early as possible, preferably before the mold is designed, before you've gone into real concept ideas. Speak with us first. It's free of charge to talk to us, get an idea of how it should be laid out, and could well save you all a lot of time if we can speak openly as early as possible, as early in the project stage as possible. And this is my last, nearly my last, or one more after that, but it's a proven system. Why Servomold? Why come to us? Well, we are a very renowned supplier for servo controllers, servo molds, servo mold equipment. Over 1,200 projects running globally, with over 800, that's quite a number, in-house controllers on the market. That's a large number of controllers. And without a doubt, the most frequently used control system in the field, injection molding applications worldwide. We're continually developing our hardware and software with the experience that we have over these 13, 14 years now, plus the years before, whilst we were still working up to becoming the name Servomold. And we do, and that's why I mentioned just now earlier, reach out to us. It's not like buying a vacuum cleaner. You really need to speak to us to find out what would be the best system for your particular application. There are so many options. Even while I'm trying to explain it now during these few slides, you can see for yourself there are so many options. It really is a very big box of Lego bricks, which we're more than happy to try and put together to fit the application that you have. So I will take it now to an end. Thank you very, very much. And again, my apologies for the very late start. I will obviously blame all the IT people for that. I'm a toolmaker and that's my prerogative. We're allowed to do that. So thank you very much. Please feel free to contact us for further information. Reach out to DME, reach out to your contact person at DME. They will reach out to us. We know there's a time zone in between us, but it always works. We're around. We'll be smiling and holding our thumb up as Christian is doing there, whatever time of the day. So thank you very much for listening. And yeah, Mark, I don't know if you want to open it up for questions and answers.
Absolutely, we have some questions here that we can get to. I want to thank you for the presentation and for going through it and being very thorough with this. And also want to thank everybody who's listening right now for sticking with us as well. If you do have questions, please put them into the chat. We will get to them. And these could be questions either for Richard at Servomold and the team or for DME as well. The first question that we have is there a default for cavities, pitching, spacing? And if so, where can we find those dimensions?
I didn't quite catch that. Is there a what on dimensions?
Is there a default for cavities, pitching, spacing?
No, that's actually quite nice. Because we're making everything from our little box of Lego bricks, the pitching, the positioning, we would do that according to whatever your requirements are. Quite often, if it's a full hot runner system and you're using an open gate or a needle valve or even a side gate, then those pitchings are going to be given to us then by the hot runner supplier. So we would be able to accommodate whatever requirements the customer has.
Perfect. All right. Second question is, have you made a mold for zinc?
For zinc?
Yes.
I'm going to say no, because I believe that's high temperature. Is this the same sort of temperature as die casting? I have to put a question back, because if it's die casting, I know we've spoken about it in the past. Of course, one can insulate and all the rest of it, but one needs to keep in mind servo motors, any servo motor, whether it's in an injection mold or in an electric car, they don't like heat. The minute they get to certain temperatures, they start to lose power. What we tend to do, if it's an injection mold with, say, 150 degrees centigrade running, we can still do that. We can put an insulating plate in between the motor, the servo motor itself, and the mold. But I think, to answer your question of zinc, and I would be more than happy for any of my colleagues to jump in and correct me if I'm wrong, but I believe zinc is too hot.
Okay. Yeah, I believe this is for die casting. Oh, I'm sorry. Someone's saying. Okay. Next questions we have also, if you guys have questions, just put them into the chat. Next question we have is, are the core controllers plug and play with Euromap 67 pin in and out wiring?
Yep. We can always help out whatever sort of connections you're going to need. I mean, it's very important, again, that you tell us exactly what machine you're going to be running on, but the Euromap would work, no problem. We just need a signal, like a core puller signal, to say, now act. And then we will give the signal back, we've done it. It's a very, very simple setup. We have obviously highly trained guys working at the factory who would be able to configure the cabling to be able to match your machine. Again, communication being extremely important. So we need to pictures. I mean, Euromap is one thing, but even on Euromaps, I've been informed, even Euromap doesn't always guarantee that you're going to be getting the cables in the exact same position they should be. But yeah, it's a very simple connection between controller and injection molding machine.
One more thing.
Supply all the cables you need. You just need us to tell us exactly what plug is on the machine, and we would ensure that you get the right, what socket, and we would supply the right plug. That's the right way around.
Exactly. And one more note for the Euromap 67. It's since it's a handling interface, it's usually not capable of doing simultaneous movements. That's one downside of the 67, but it works in general. It's absolutely no problem. But yeah, that's just another note on this particular interface or this particular plug.
All right, good deal. Again, if you guys have questions, please put them into the chat and we'll get to them. Next question we have is, what are the lead times like on repair parts, and do you recommend any spare parts?
Good question. Very good question. Lead times, of course, it always depends what it is. From a very small single system, single core with a motor that's perhaps already on stock and a gearbox, lead times can be down to 8 to 10 weeks. For a more complex system, obviously, then that time is going to go up depending on the scope of exactly what we're supplying. And to answer the second part, yes, we do suggest spare parts. I know that in the medical industry, there's usually a requirement of 25% anyway, particularly on any foam mold, plastic touching parts, so cores and cavities. And where a core is going to be the unscrewing core, the thread, then obviously we would recommend a 25% purchase on spares, because we wouldn't be making a huge amount of specific mold giving components. We wouldn't make a lot of those on stock because they're specifically for that one customer. But of course, when it comes to bearings and gear wheels and certain parts which are pretty well standardized, or the cooling cores, for example, the cooling tubes, rotational cooling tubes, these sort of parts are then standard and they can be supplied quite quickly. But if it's something that's specific to that one application, highly recommend the manufacturer of spare parts. And if there aren't, then the lead time is not going to be that short. So it is important to keep that in mind. Yes, we would recommend that.
Great. Also, just to let everyone know, we will be sharing this webinar afterwards. Probably within a couple days or so after the webinar, you could expect an email from DME with a copy of this recording. Another question we have is, can you use one controller on several different molds? Can you change from one product to another?
Yes, you can. As I mentioned, the Mini, that can only control one motor. But if you have half a dozen molds and each one has one motor, then you can have half a dozen programs. You can have up to 100 programs. You can have 100 individual molds with one servo motor on it. If, however, you have a mold with 2 servos on it, then of course you're going to need a standard. And this is why we tend to recommend, we've seen that actually coming up more, that customers would buy the standard anyway, even if they only have the 1 motor, because it gives them the option to buy a second regular card amplifier to be able to control a second motor if you have 2 motors running at the same time. I would also go back that 1 mini controller can only do 1 mold at a time. You can't have a machine next to each other and have 1 controller running then 2 molds. That wouldn't work. Can only run 1 servo motor at one time.
And at some point we have a bit of a sizing issue as well. It's kind of hard to use the same amplifier for a 2-cavity unscrewing system and for a 126 cavities unscrewing mold. At some point we're getting a bit of a sizing difference, so there are different sizes of controllers as well, but with our standard units you're able to control like 95% of the applications usually.
Thanks, Christian.
Okay. Next question we have is, what is the max temperature of your systems?
We usually say 60 degrees of the motor. The motors don't like to go over 60 degrees, and that's where we put then an insulating plate in between the motor and the mold. We have several systems where we're running peak. Molds are running very, very hot, well over 100, 150 degrees centigrade. This is not an issue, but then we would need an insulating plate with even a cooling manifold in between. And we can run some cold water in a little manifold in between the motor and the mold so that the motors don't get too hot. As I mentioned before, they don't like heat, but if we keep them insulated, then there's no issues whatsoever. And that's why we need to know way in advance what sort of mold you're going to be building, what sort of resin and what temperatures you're going to be running at.
So more of a reason to get with the DME rep and you to figure out what we want.
Right.
Can you explain about the maintenance intervals and part depreciation rate?
Maintenance intervals and what?
The maintenance intervals and the parts depreciation rate.
Parts depreciation. Not too sure what one means by parts depreciation. Maintenance intervals. For example, actually, that case study that we've just shown there, I'm rather lucky that I was actually involved with some discussions with the customer only a couple of months ago. They do an interval of 300,000 cycles. Every 300,000, they'll pull the moving half out of the machine, just take the back plate off, clean it up, make sure nothing's happened. Now, maintenance intervals are very, very difficult to say in advance how often you should do it. It really does depend who's using it and how they're being used, if they're really being correctly looked after. If, for example, and this actually happened to a particular system we were looking at a while back, water managed to get into the gearbox without anyone knowing. If you go over that 300,000, I mean, this 300,000, they basically said, okay, we do a check then. Quite often, it would be taken out of the machine, take the back plate off, have a look. Everything is perfect. There's been no water ingress. There's been no out of alignment. Everything has sat where it should be. Then you put it back together and carry on running. One needs to inspect it just to be on the safe side. But if water can get in, and water is obviously a disaster for a nice, very highly accurate, high precision gearbox using caged roller bearings, caged needle bearings, all of these cores are located and supported over needle bearings. They're very, very fine. They're very small. So of course they need to be looked after. You have to put in the right fat, the right grease, and they need to be well maintained. But as far as part depreciation, I'm not too sure what we're talking about there. We have again here in Switzerland, we have molds running for years, and parts only get swapped over like bearings, seals, or maybe even some needle bearings would be changed over as a matter of course, just on a safety level. But that would be maybe 500,000 or even 1 million cycles before that's actually necessary. It's more of a learning curve because, as I mentioned, each unit is usually, or each system tends to be project based. So to look back on them and say, well, we know exactly what that one's going to need is very, very difficult. If it's a repeat, like the case studies that we've shown and we know, yeah, they run for years, they check it every 300,000, then it's easy to say 300,000 would be fine. But otherwise, it's a case of check more often than you think would perhaps be necessary. And then you can, if you see and you check and everything's inside is fine, then wait a little bit longer and then you can increase that level of time between each maintenance. It's a sort of learning by doing phase, unfortunately.
Yeah. Okay, if anybody has any other questions, we have one more kind of a situation and challenge here. So, so if you have any questions, please put them in the chat. So this one is an experience that a user had with a servo unscrewing mold. The servo was specified correctly for torque, but only worked until the tool temperature came up to the mold saturation point, then freezing up the gear functionality and forcing a redesign. The question is, how do you mitigate this possibility before the tool build?
Yeah, I understood the question. I'm just wanting to check. I'm going to ask back on, is this what was this a particular system that we've supplied? Are we talking about from experience here?
They didn't really say anything on that. So I think this might just be more of a, how do you, what information do you need to stop this kind of?
Exactly. Well, like that's what we, at the very, very beginning, I mentioned that we do this calculation. We do the calculation with cold material. We'll take this formula that we have. We'll take the resin that you have. We'll put in the design, the sizing that you've given us with the 3D part file. And then we would make the calculation, the shrinkage calculation. Obviously, we put in a little bit of safety and we would put in a bit of our own experience of exactly what resin that was. But we calculate the cold forces required. That's how we mitigate it. We have the calculation of the materials and we know with that calculation how much torque is required. We have a program to calculate it. That's our mitigation right at the very beginning.
Okay, great. And then last question we have right now is, what is the warranty time offered for the complete servo mold and controller solution?
Well, that's Christian, could you help me out on that one?
Again, sorry, I didn't quite catch the first part.
Guarantee?
The warranty time offered for the complete servo mold and controller solution.
The guarantee.
Yeah.
The warranty is, it depends. Usually we have the standard 24 months on our controllers, which is obviously a European standard, I think. We have to guarantee 24 months of general function. And then it depends a bit on of course, the controller itself is not under any stress in this case. So we don't have like a cycle guarantees or something. But for our mechanical parts, for the unscrewing halves, for example, we offer various guarantee or warranty packages for up to, I think, 8 million cycles. And for all our unscrewing units, which we just implement in the customer's mold, because there are many factors we can't control 100%, we usually guarantee it's either 2 million shots or 1 year of production, whatever comes first.
Okay.
That's our standard warranty, what we give out for our systems.
Okay, so for more details, get with the DME rep and what you're looking for and what do you want to build.
Exactly.
We'll figure it out for you.
In a nutshell, controllers are 2 years. Unscrewing units is 1 year. or 2 million cycles, whatever comes first. But as Christian very rightly pointed out, there are so many different options. It's very rare that we're making the exact same thing over and over again, other than, of course, our linear controllers, our linear actuators. It's a different story altogether. But there, obviously, we would, it is on a case-to-case basis.
Yeah, which just proves the power of the Servomold line. You could just create whatever you need for that. So that is all the questions that we have for right now. Thank you, Richard and team, for everything that you guys done and got it. This presentation. Thank you to everybody who stayed online as well and listened to all the questions and answers. We will be sending out a copy of this presentation to you via email within the next couple days or so. But with that, I guess that concludes the presentation. Thank you, everybody. Thank you, everybody who's in the United States. Enjoy your long extended weekend. And we will see you next month. I believe we will be talking about our hot runners at DME, and Jeremy Such will be on board talking about all the hot runner information that we have available for DME. So thank you again for everybody, and we'll see you next month.
Thanks very much, Mark, and thank you also my team for getting this all together. And my apologies for the technical hiccup at the beginning. Bye-bye.
It all worked out well. So thank you again.
Good. Thanks.
All right, take care, guys.
And you. Bye.
Thank you. Bye-bye.